the time reversal invariance of physical laws is often suggested to be a problem for the fundamental directionality of time. So again, this brings us back to something else you said, the distinction between representation and object. But what is time reversal invariance, and why does it not pose a problem for the fundamental directionality or fundamentality that you believe time to possess?
So let's talk for a minute about the kind of invariance people mean in general before we get to time reversal invariance. So usually what's meant by a physical invariance or a physical symmetry is that if the laws of physics allow for something to happen, then there are certain systematic changes you can make. And you'll say the laws of physics, if they allow for this, they have to allow for that. Here's an obvious one, what's called rotational symmetry, at least at the level of the lab. Okay? So, I do an experiment, and I'm going to assume, which might not be true, but for these purposes, that the lab is kind of isolated from what's outside the lab, because I'm not going to be able to impose this symmetry over the entire universe. I can only do it in the lab. But imagine I do an experiment, and that assumption might not be true. You have to be a little careful here. Just to take a concrete example, we all know about the Michelson-Morley experiment. We've talked about that. At one point I said it's an interesting experiment to describe. One of the interesting things about it was they carried it out. They had an apparatus. They had an apparatus that was taking light and splitting it and sending it two different directions and recombining it to get these interference bands. But the entire apparatus was sitting on a big stone disc, and that big stone disc was floating in a pool of mercury. Why? Because they wanted to be able to take this apparatus and turn it, rotate it, right? So I'm going to set it up this way, run my experiment, take some data. Then I'm going to turn it 90 degrees, run the experiment, take the data, right? Now, in most cases, what you would expect is that the data will look the same. Now, of course, that's not always true. If I just put a compass needle there because of the ambient magnetic field of the Earth, it wouldn't look the same, right? But again, we're assuming that somehow we can shield the lab. I mean, we could even put metal around it so the magnetic field of the Earth doesn't penetrate into the lab or whatever. But you think the kind of, suppose I've got the laws of physics, and suppose I imagine, according to the laws of physics, the situation where there's just no magnetic field. There's nothing outside the lab. The lab is sort of all there is in the universe. The rest of it's vacuum, that's empty. Do the laws of physics say that if I rotate the system, that there'll be, you'll get the same data, essentially? We normally think that's what you'd expect. In fact, what we think is that if that doesn't happen, then it's your obligation as a physicist to find out what is this thing you're not taking account of, right? So this is how you might discover there is a magnetic field, is because, wait, I've got this little thing in my hand and I turn it like this, but the little pointy thing doesn't turn, right? It keeps pointing this way. That's just an indication that I haven't yet accounted for everything. There must be something that's, as it were, determining that it aligns this way. Of course, we think that if we were to rotate the entire Earth, the magnetic field would rotate with it. And again, now the results would show up the same in the data. So that's basically what a symmetry is, right? A symmetry is supposed to be a transformation of the physical situation that doesn't create any qualitative or observable difference. And we typically think that space is isotropic, which means if we were to rotate everything relevant, nothing would change. And homogeneous, which is that if I do the experiment here and then I pick it up and just plunk it down over there and do the experiment, I should get the same result. Again, that doesn't always happen, but when it doesn't, I think that's a failure of physics. I'm going to say, gee, if I do the experiment here and it comes out one way, and I do the experiment here and it comes out a different way, there must be something physically different between these two locations, right? There must be something going on. And I ought to figure out what that is, right? This is a kind of methodological demand. And nobody would kind of be very happy to say, no, there's no difference at all. I mean, that would more or less be the end of physics. Okay, so there are all of these symmetries. We've got rotational symmetries. We've got translational symmetries. Galilean symmetry is fancier, right? Galilean symmetry, we've talked about. Do a bunch of experiments in a boat that's at anchor in a harbor, record the outcomes. You're jumping around and you've got these flying, insects and so on, dripping water. Now put the boat in motion, but on a calm sea, so it's moving in a straight line at a uniform rate. All the same, it'll look all the same. That was supposed to be a symmetry in the phenomena for Galileo. So what's time reversal symmetry? Well, it would better be called, classically, time derivative reversal symmetry. Not time reversal symmetry, but time derivative reversal symmetry. What do I mean by a time derivative? Well, the usual time derivative, the one you're familiar with, is velocity, right? I have an object moving like this, all right? So it's constantly changing its position. It's got a velocity. Reverse the velocity. Okay, I mean, instead of going this way, have it go this way, right? That's a change. It's like rotating this or moving this. Try and take all of the moving pieces or changing pieces of a situation and reverse their time derivatives, reverse how they're changing. If they were going upward, now make them go downward. If they were going to the right, now make them go to the left. Now, what happens with time reversal symmetry is the following claim. Take an initial state of a system, let it evolve through time to a final state, right? And the final state could be very different from the initial state, right? All kinds of stuff going on in between. Now, take that final state, time reverse it, time derivative reverse it, and make it now the initial state and let it evolve. And the idea is that if the laws have time reversal or time derivative reversal invariance, then the final state, when I reverse the derivatives, will evolve over the same period of time to the time reverse of my original initial state. And that was a little complicated, so let me say it again. I have an initial state, a final state, Ti, Tf. I have a time derivative reversal operator. I say, okay, take Tf, take the final state of my experiment, reverse the time derivatives, and make that now the initial state of a new experiment. If the laws have time reversal invariance, that will evolve forward in time to the time reverse, to the time derivative reversal of my original initial state. So I go from here to here, plunk this down here, reverse all the time derivatives, let it evolve, and then this should be now the reversal of that. That's what the symmetry is. That you can look at some laws of nature and say they would have that symmetry. Newton's laws, F equals ma, have that symmetry, right? So if you say if the fundamental dynamical laws are Newton, it will have that symmetry. Does that mean time doesn't have a direction? No. Newton knew they had that symmetry. Newton thought time had a direction. I mean, it's just crazy to think the existence of that symmetry suggests that time itself doesn't have a direction, A. B, ironically, in quantum theory, it doesn't have that symmetry. Okay, so that very symmetry, which Newton is in Newton's physics, is in Maxwellian electrodynamics, has that symmetry. It goes away in quantum mechanics. In quantum mechanics, if you're doing quantum field theory, it's believed, it's postulated that there is a fundamental symmetry of the equations that's called CPT. CPT means you don't just do one thing, like we've talked about, just twist it or move it or do this. CPT means you do three things. C is charge conjugation, so you replace all your particles with antiparticles. P is parity, so you replace your laboratory with a mirror image. So that's, right-handed screws become left-handed screws. And T is our time derivative reversal, time reversal operator. Okay? So what is said is that in quantum field theory, it has CPT symmetry. If you do all three of those things, you will get it'll continue to obey the equations of motion, the fundamental equations.